طيب بسم الله الرحمن الرحيم. So last time we talked about traffic policing mechanism, and we covered two major mechanisms. One is leaky bucket, and we said that leaky bucket constrains the bit rate, but the problem is that it maintains the maximum rate as fixed rate, and that does not align very well with the fact that some multimedia applications require by default variable bitrate, which produces constant quality, and by constraining the maximum bitrate to a fixed rate, we actually can get variable quality in terms of multimedia applications, and that's in some cases not desirable. So token bucket tries to resolve that problem by tolerating certain bursts using the concept of a bucket filled with some tokens, and if you send with a variable rate less than the token rate, then you build some credit which allows you later on, if you have a burst, you can consume your credit, and this way we can tolerate small chunks of bursts every once in a while, but not all the time, of course. So we have to also constrain the some multimedia applications not to consume the entire bandwidth. So we have to have some policing, and the policing here happens if you consume all your credit, then it's a problem, and you have to wait, or you have to regulate the traffic rate. So this, in fact, may lead to constant quality in terms of multimedia applications, which is more desirable compared to the leaky bucket. So starting from today, we will talk about some enabling protocols. So until now, we've been talking about mechanisms and fundamental definitions and things like that. But these mechanisms, in order to be put into operation, they require some protocols to send back and forth some messages. So quality of service requires a protocol in the network layer, which is what we call resource reservation and signaling mechanisms. These are actually not mechanisms. These are actually protocols. They send messages between the source and the intermediate routers and the nodes in the network in order to facilitate the provisioning of the resources at every point. So in order for us to be able to perform classification on a certain flow or a certain application, assign specific priority in terms of channel access mechanism, or assign a certain priority in terms of queuing and so on. This requires the fact that at the beginning we need to know the requirements of that application. Okay, so first the application needs to send its own requirements, and it flows through the network, and the network will, at every hop, will start to estimate, based on the traffic requirements, it starts to estimate what would be the queuing behavior, what is the channel access behavior, what is the, if I need to do some traffic policing, if I need to do this and that. And then it has to propagate this agreement across the network, and based on this, the application starts to encounter certain behavior. So this is the summary of today's talk. So resource reservation and signaling, it's used to provision the resources through some signaling. By signaling, we mean like small messages that the application uses to define its own requirements. So I require certain bandwidth, I require certain guarantees, maximum delay, minimum bandwidth, maximum dropping probability, something like that. And also it defines whether it needs some kind of qualitative quality of service, quantitative quality of service, things like this. So it defines this in a message or a signal, and this message will be used by this protocol to be sent across the network, as we will see in a minute. So at every hub, including the source, at every hub has to estimate, based on these requirements, what kind of resources do I need to reserve for this particular multimedia application. Okay, we didn't have to do this for the base internet. So base internet without quality of service support, we didn't have to do that, right? So we didn't do this, but now we have to do this to provide any kind of service differentiation, whether qualitative or quantitative. So the delivery of the quality of service requirements, as I said, it goes through the network and it gets received by admission control mechanisms and classification mechanisms and channel access mechanisms and so on. Okay, so these requirements will have to be mapped into specific behavior on each of these mechanisms, as we will see in a minute. So, for example, the admission control block will receive the requirements of the application, and based on some calculations and estimations, it says there's no way I can reserve enough resources for this multimedia application based on its requirements. So what is the outcome? I should reject it, because if I admit it to the network, then it will affect negatively all the other resources. So I should actually, from the beginning, I should reject it. Or if I accept it, then it goes to the classifier. The classifier will say, based on these requirements, I can put this application in this quality of service level, or in other words, in this priority, okay, or in this queue. And then after that, the channel access mechanism will say, okay, so based on these requirements, I should actually specify certain priority, which, as we said, it gets controlled by the back-off delay that I have to wait from the channel point of view, as we will explain even later in more details. So if the resource reservation and signaling sends this quality of service requirements through the network, and the admission control block concludes that I cannot admit this traffic, then it sends a notification also as part of this protocol. It sends a notification back to the source to stop the source from sending any traffic, because there's no way we can admit this traffic at this point in time, because I cannot guarantee any level of quality of service for that traffic if it goes into the network. So this is how it looks like from the overall picture. So at the sender level, the sender initiates the resource reservation process by sending the traffic requirements of the application into the network, and it goes through the intermediate host. This host could be a router, could be a switch, could be anything. Okay, and again, the resource reservation block will pick this signal or this message, and then estimate from the requirements of that application, estimates what should be the behavior, okay, from the network point of view. And then the same message goes across each hub until it reaches to the receiver. The only difference between the sender and the intermediate hosts, including the routers and switches, is that the admission control block. The admission control block is the one that rejects or accepts to admit the traffic into the network. Okay, so that typically happens from the network point of view, not from the sender point of view. واضح كده? So admitting or not admitting the traffic comes from the network point of view. So the network will estimate what would be the amount of resources that this traffic needs, And do I have these resources from the network point of view or not? If the answer is no, then I send a notification back through the same protocol. I send a message back to say, I cannot admit this traffic at this point in time. Okay? And we said that admitting or rejecting the traffic is part of the quality of service, right? It's not that because this traffic has low priority. No. What I'm trying to do here is that I'm trying to guarantee a certain quality of service level for that traffic. If I cannot provide these guarantees at the moment, it's better for the traffic to wait for a certain period of time, and then when I have the proper resources, I can admit it back into the network. Resources means in terms of channel capacity, in terms of buffer in the router, in terms of which queue I should assign this traffic to. Because depending on all these things, the traffic will encounter certain behavior. Whether this behavior is very good in favor of this traffic, or it puts this traffic as at a very low priority, in which case it will get low resources from the network. That's what I mean by resources is an abstract word, but it actually means what kind of buffering I should do, what kind of queuing, traffic handling, and so on. Okay? So the dotted lines here represent the control or the signaling information. Okay? Through these signaling information that flows through the network, then I can guarantee certain behavior for the traffic itself. Okay? So the traffic itself is here. So the traffic goes in here, and this is the solid line. So the traffic should go this way. So in order for me to guarantee certain behavior for this traffic when it goes through the network, I need to perform some signaling first through these dotted lines to prepare the network to receive the traffic from this multimedia application and guarantee certain behavior for this multimedia application. So there is a philosophical point here. This is from the network point of view, right? What is the difference between this and the virtual circuit or circuit switch network? Because what we are essentially trying to do here is that we are preparing the network to receive the traffic, right? So are we completely back to being like circuit switched or not?
No, because we have many senders that will use the same channel. But in the circuit switch, we'll use only from one sender to one receiver. It's dedicated for one.
Yes, bravo, Alik. Yeah, that's a very close answer. Yes, again here, we don't necessarily have to reserve these resources for a sender to a receiver end-to-end connection. No, this is to reserve certain resources for certain level of quality of service, which could be like per class, which might actually group multiple flows together, regardless of the end-to-end connection. Okay, so this has to be very clear. In other words, here we're not actually establishing a circuit. We didn't talk anything here about establishing a circuit. What we are trying to do is that we are trying to make sure that the resources in the network is fit for the requirements of these applications. And if they don't fit, then we can say, we reject this application, stay away at the moment, and later on you can get into the network. But we did not talk about establishing an end-to-end circuit. In other words, this type of signaling does not guarantee, for example, the order of the packets to arrive at certain order, because again, we're not actually establishing any circuit. Okay, so establishing a circuit will lead to a ordered transmission, will lead to providing quantitative quality of service, and so on. Because when we establish the circuit, we can guarantee everything. Everything is deterministic. It's like, more or less, we are connecting a wire between the source and the destination, although this wire actually crosses some network routers and stuff. But it's as if we are connecting a wire between the source and... Here, we're not doing that. Okay? We're not, again, guaranteeing the end-to-end behavior. All we are doing is that locally, we are trying to prepare ourselves for what's coming. And if there is no way we can accommodate what's coming, then we should notify somebody to say, I cannot admit this at this point in time. Okay? But there is no guarantee end-to-end. That's why, again, until today, the only way to provide quantitative quality of service over packet switched networks is over provisioning. We have to see the worst case, and we have to establish a virtual circuit like over packet switched networks.
But still need the optimization of the capacity of the channel.
Exactly. Bravo. That's a very good point. But here, we are addressing the trade-off between providing good quality of service and best utilization for network resources. Because always providing quantitative quality of service comes with a cost. Wasting more resources in the network. So here, we're trying to do that efficiently by addressing the trade-off between providing good level, close to quantitative, although not 100%, but utilizing the network resources really efficiently. Okay? Any questions? So that's the big picture. So that sort of ties some of the techniques that we have discussed so far, and we will see in the next figure all the techniques and all the mechanisms working and integrated nicely together. So admission control is done in two ways, either explicit, and in the explicit admission control, we have to conduct an explicit resource reservation, which means that the requirements of the application has to go through every single hub through the end-to-end path. And then at every hub, there has to be an answer for this question. Can you accommodate this or not? If the answer is no, then it doesn't go further. It just goes back and notifies the traffic that no, you cannot get admitted into the network at this point in time. That's it. So that's explicit. Okay? In the implicit admission control, I don't have to do this. I don't have to do the yes and no thing. Okay? In that case, the admission control mechanism is done indirectly through some traffic policing and over-provisioning. In other words, it's not like I get the requirements and then I estimate and say yes or no. No, it doesn't work this way. Implicitly, which means that I remove admission control, I remove the explicit admission control, and I rely on the fact that I do certain estimation for the traffic, which means I do over-provisioning. And then based on this over-provisioning, I have, like, for example, the traffic says that, okay, I have average rate of 200 kilobits per second, but the maximum bit rate is 500 kilobits per second. So what do? I reserve 500 kilobits per second. This is over-provisioning, okay, which means that the network will be underutilized. Okay, so what if the traffic goes above 500 kilobits per second? Is that possible? Well, it's possible. Theoretically speaking, it's possible. The traffic tells me that the maximum bit rate is 500 kilobits per second, and at a certain point, it goes beyond 500 kilobits per second. Okay, so in that case, in order to make sure that the traffic is well behaving, in that case, I can use traffic policing together with over-provision. I didn't do any yes and no thing. I didn't do any explicit admission control in that case. Okay? But I can make sure that this traffic abides by this bitrate bound through some traffic policing. So I can use like some kind of leaky bucket and with a maximum rate of 500 kilobits per second. And this way I can make sure that the traffic will never go beyond that. And this happens at the source. I can actually apply this right at the source. So I make sure that the traffic will never go beyond 500 kilobits per second. So in that case, I didn't do any explicit admission control, but I did some what they call implicit admission control. So I admitted the traffic, but according to my rules. Okay? So I can admit you, but according to my rules. Do not go beyond what I can allocate for you. So I can do some over-provisioning for you, but you should never go beyond that. Okay?
So that does not mean that explicit admission control will more satisfy the quality of service request. Like in the implicit, it does not look to the application if it has quality of service requirements or not, right? It's policy.
It does. For the implicit admission control, it does look at the requirements of the application, but it does not reject or admit. Okay? It does not reject or accept the traffic. It just makes sure that this traffic will be well behaving when it goes through the network. Okay? Explicit admission control will provide quality of service overall for the entire traffic, because the ones that get admitted into the network will surely have the quality of service that I can guarantee. Because if not, then I will reject. So I take only the number of applications or the amount of traffic which I can really handle. Above that, I cannot, I will reject the remaining ones. Okay? So that's the, okay, so in terms of quality of service architecture, there is like 3 levels of providing this quality of service. As we said before, applications with quantitative quality of service requirements. So what do I do, what do I need to do from the network point of view, okay, in terms of the mechanisms that we have studied so far? How can I connect the dots, connect the pieces, in order to make sure that the applications with quantitative quality of service will get as close as possible to what they want? So that requires guaranteed quality of service. So some quality of service architecture like NServe, integrated services, the one that we have discussed before, which provides possibly per flow behavior. Again, this is not scalable, but this is part of providing quantitative quality of service. Because again, grouping the flows together will not guarantee any service differentiation between these flows together. Because if I group all the flows into one class, I provide behavior per class, not per flow. So in that case, they get mingled and mixed together. So, so quantitative quality of service requires possibly a framework like integrated services. It requires explicit resource reservation, right? Because in that case, I know exactly who gets admitted into the network, so I have full control who gets into the network. So in that case, I can provide some quantitative quality, possibly some quantitative quality of service. And it also requires some strict traffic control, including what? Including like something like strict priority queues. Okay, so remember strict priority queues. So we have the high priority queues will have to go first all the time. Okay, so in that case, I can provide quantitative quality of service for this category of queues. And of course, traffic policing. So traffic policing, I can use either token bucket or leaky bucket to again make sure that the traffic is behaving. Possibly here, token bucket will be more efficient in that case. Okay, to again accommodate some bursts, because leaky bucket, the problem with leaky bucket is that it transforms the traffic by constraining a certain by a certain rate, certain maximum rate. Whereas token bucket has some tolerance in terms of providing or accommodating more bursts in the traffic. So it does not change much in the traffic itself. As we said before, it does not change much. But token bucket, leaky bucket really transforms the traffic frequently by constraining the maximum rate.
For the implicit admission, does it mean it's more flexible kind of admission, so it can do over?
More loose. It's loose. It's loose. It's not like very harsh. It's loose. It doesn't say yes or no. It's not binary. It admits everyone. Yeah, it's more accommodative, more inclusive. But the problem with that is that if you are inclusive to everyone, you can never satisfy everyone. Yani when you have many traffic into the network and you admit everything, of course, even with some level of control, like traffic policing. So you use some traffic policing. So from that perspective, you have some control, but you never say no. Okay?
But there will be side effects on the network.
There will be side effects on the network, exactly. So there will be side effects on the network. So possibly with no explicit admission control, it's very, it's not impossible, but it's very hard to provide quantitative quality of service. Because again, not having admission control will loosen your control over what traffic gets into the network. You always say yes, but you say, okay, you get in, but with some rules. But so you have control over the amount of traffic per application. But you don't have control how many applications use the network. Because you never say no, right? So in that case, you admit many applications. So after some time, you may actually lose control over who is actually using the resources of the network at this point in time. So after some time, you cannot provide any guarantees. You can provide qualitative, but not quantitative. So you can say, I can guarantee that certain multimedia applications will encounter better performance compared to others. But the fact that you never say no makes the number of applications enter into the network in an uncontrollable way. So at infinity, of course, you will have a problem, right? Explicit, no. For explicit, you accept certain number and then you say no, stop, I cannot get any more. So you have full control over who accesses the resources of the network. You have extremely full control. Because you have control using traffic policing, you can control the amount of traffic per application. Right? And admission control will also allow you to control the number of applications that access the network. So you have full control over the number and the traffic per application. So everything is under control. So in that case, you can provide some quantitative quality service in that case.
Okay, on the other hand, is there some cases that implicit admission is preferred, like significantly preferred?
Of course, because it's for resource utilization, for the utilization of the network, okay, versus the number of users or the number of applications provided, it's better because it never says no. Okay, so imagine this imaginary scenario. So a network has explicit admission control, and we have homogeneous type of traffic, and you have multimedia applications, N multimedia applications. Each one requires 100 kilobits per second. Okay, and the network can accept, let's say, 1,000. So how many multimedia applications you will accept? Using explicit admission control, you will stop at 10 and say, I cannot accept anymore. I cannot accept anymore, right? So using implicit, you will accept all of them. All you will have control of is the fact that each one will never go beyond 100 kilobits per second. but you can accept 11, you can accept 15, you can accept 20. So after some time, so imagine like a network that can handle 10 of these multimedia applications, so you can potentially grow to 20 or 30. So imagine the type of quality of service or the type of behavior that each one will get. Of course, the quality will drop. Okay. That's why for implicit admission control, it's maybe better from the network resource utilization point of view, right? Because you may actually admit 12 or 13 or 15 traffic, and they are still getting some acceptable quality of service. We don't know. So instead of stopping at 10, at least now we can allow 11th and 12th, 13th and 14th. Whether this is good or bad, it depends. Okay? So that's in that level. If you want to provide quantitative quality of service for applications with quantitative quality of service requirements, then we need something like explicit admission control. We need something like strict priority queues. Okay, we need some framework that provides per flow to guarantee the behavior per flow and so on. The next level is applications with qualitative quality of service. So in that case, definitely explicit admission control is not required. So we can say that. Okay, that, by the way, constitutes more than 95% of the internet traffic. So that level here. Okay, more than 95% of the internet traffic follows into that category. Okay. So it requires high quality of service in terms of service differentiation, but no requirement in terms of providing quantitative quality of service per flow. So in that case, definitely for traffic handling, for queuing, what type of queue do you think would fit in that category? Other than FIFO here. Okay, this is FIFO. Okay, and we said this is a strict priority queue. So what's remaining? Lower. No one remembers. ده حكى عندنا امتحان. بس ما كانش داخل في الامتحان ده. اوكي. ايه اسمه ايه؟ weighted fair queuing. برافو عليك. Okay. At least she's digging into the memory to try to get the information out. Okay, that's perfectly right. So weighted fair queuing provides that compromise. It allows you to provide qualitative quality of service. So the ones with higher weights, the queues that gets assigned higher weights will definitely have better performance and better behavior compared to the queues that has low weights. So we know that. So this is the basic definition of qualitative quality of service. Okay? So that's how we tie these mechanisms that we have studied before. We can tie them together. We can connect the dots to say, okay, so if we want to provide quantitative quality of service, we need explicit admission control, we need strict priority queues, we need this type of traffic handling, and so on. Okay? And best effort, as you said, a FIFO would do. Okay? And no, of course, no explicit admission control in that case. You don't have to do much of what we have talked about so far. Okay? So there's no service differentiation anyway. Okay? So this is the big picture. So this is how the architecture looks like if we were to talk about wireless infrastructure-based wireless network. So in that case, a router is an access point. So the network for us is the access point. This is the one that admits traffic. This is the one that performs the traffic handling and so on. So we do the reservation, resource reservation. So you have, so the dotted one here is the signaling traffic. The signaling traffic is the control traffic. The control traffic that you need to send messages back and forth to prepare the network for the traffic that it's coming. Okay? So the resource reservation at the source at the wireless node will send to the access point, I have this quality of service requirements. And then the access point will say, okay, can I admit this or not? If the answer is yes, then it sends, okay, go ahead. But here we have to make sure that the classification is providing certain behavior. We need to do some traffic policing to make sure that the traffic is well behaving, and then put it in a specific queue, and then use the proper packet scheduling, whether weighted fair queuing if we want to provide qualitative, or maybe strict priority queue if we want to provide quantitative, and so on. Okay, and then channel access. For channel access, as we said before, we control the priority. That's another level. So packet scheduling here gives us the intra-station packet handling. So that inside one station. Channel access mechanism gives us the interstation. Okay, interstation channel access. So between this station and this station, who will have access to that channel? Well, the one that has lower or shorter back-off delay, for example, if we were to use SESMA CA, the one that uses shorter back-off delay is the one that will have access to the channel more, because this one will implicitly have more priority to access that channel. So by controlling this priority and controlling the packet scheduling and controlling the traffic policing and classification, all of this have to work hand in hand to provide certain behavior, whether it's qualitative, quantitative, or best effort. Of course, for best effort, I can bypass all of this. I don't have to have any control here, and the traffic will go, and ربنا وفقه goes into whatever behavior it encounters. I don't provide any guarantees. Exact same architecture happens in ad hoc, even in wireless ad hoc network. If we want to provide some kind of quality of service behavior for these wireless architectures, we will study them in more details later on. But the exact same architecture applies for the case of wireless ad hoc. What is the difference between ad hoc and infrastructure? No, not really. No. Without access point. Bluetooth is some kind of ad hoc wireless standard. So it does not require any access point. Okay, so in that case, there is no access point in the picture. So there is no centralized controller, in other words. But for providing quality of service, if you want to have admission control, then you have to have a designated node to virtually represent an access point. Although it's not an access point, it's one of the points. It's one of the nodes that communicate over the ad hoc network. But it's designated to perform the function that is otherwise done by the network, which is admission control. So if we are, like for example, in a mall, and we have our cell phone devices, there's no access point. We can communicate directly using Bluetooth or something like that. So we have N nodes. So we have to agree on one of these nodes to be designated as a coordinator node. And the coordinator node performs some extra functions. One of them is admission control. If we want to provide quality of service in this ad hoc network. Okay? So in other words, ad hoc does not have an infrastructure, does not have an access point. But if we want to provide quality of service, then we do have to designate one of these nodes to act as a coordinator for us. Okay. Although there is no dedicated infrastructure like an access point. So we don't have a dedicated infrastructure like this. We can communicate directly. So we have to nominate, which is when you pair Bluetooth, there is always one node called a master node and slave node. Okay? So the master node is by default this designated node which conducts admission control in addition to other network functions, of course, but we have to nominate one of us to be the coordinator. And in that case, this coordinator will be one of the nodes that's moving around normally, but it performs the coordinator function. Okay? Any questions? I forgot what it stands for. والله حاجة زي يعني مش ممكن تكون base station. I tried to. It's in the book. If you look for it in the book, you will find it. But so, in any case, you can call it a coordinator. You can call it a master node. You can call it whatever. It's one labeled node that performs an extra network function other than the other nodes that only communicate, and that's it. So this extra node will have an extra block which is admission control. That's it.
دكتور في possibility إنه الماستر يكون عنده quality of service أعلى من السلافs ولا راح يكون نفس الشيء؟ لأنه هو الكوردينيتور فممكن يعني ياخذ
يدي فيفر لنفسه يعني. ممكن. بس that's why we need to have standards. That's why we need to have protocols. The protocols will have to be designed in such a way that guarantees certain quality of service for everyone, and there has to be some kind of fairness. Okay. Any questions? So I was debating with myself because the book does not give any examples about protocols in the transport layer that provide quality of service. So this year, out of tradition, I wanted to include a small part which talks about quality of service in the transport layer. Because here in the book, we discussed this is the network layer kind of protocols, and it's very abstract, by the way. The network layer quality of service requires a course on its own. Okay, but it goes directly to the data link layer and the wireless access mechanisms and discusses that in details, but it doesn't actually give any idea about transport layer quality of service protocols. I noticed that in some of the groups for the project they use real-time protocol and these kind of things as part of the simulation. So I will try to put together some small set of slides about transport layer protocols that are used to provide quality of service. Okay, so I will prepare this today or tomorrow. It's not that major, but I'm warning you because this is not part of the book. So it will be an extra, and I will give you the reference where, if you want to study in more details this part, where to refer to. Okay.